Okay, so your lesson 5.2 looks at conservation of momentum. Okay, much like conservation of energy, what it says is basically the total momentum that you have initially in your system has to equal that total momentum that you have finally in the system. Okay, so if you have multiple objects, then you need to look at the momentum of all of those objects before and look at the momentum of all of those objects after to look at either the speed or how the velocities change in those objects from before to after or vice versa. Okay, so here in example 5.2.1, we have a particle of mass 4 kilograms initially moving with a velocity of 2 meters per second collides and sticks to a particle of mass 6 kilograms, initially moving with a velocity of -4 meters per second. What are the velocities of the two particles after the collision? Okay, so for the 2 meters per second, since it's positive, we'll call that forward. And then -4 meters per second, since that's negative, we'll call that backwards. Okay, so now we're looking at conservation of momentum. So the momentum initially means we're going to look at, we'll call this M1, and we'll call this M2. Okay, so before I get started, what I usually say to do, especially with these problems, because when we get into multiple objects and looking at collisions, you're going to want to have like your given values. So I would always say to make sure that you just, for this one, kind of follow your grass method, because it is going to get a little bit confusing with all of the like variables and M1s and VI1s and VF1s that we're going to have. Okay, so M1 is 4 kilograms and it has an initial velocity, so we're not going to call it V1I, we're going to call it VI1, sorry. Is positive 2 meters per second. Okay. M2 is our 6 kilograms. And it has an initial velocity of -4 meters per second. Okay, so much like we do with forces and everything, notice I've kind of already signified my directions of my velocities here, right? So I don't really need to carry those directions forward when I'm going to solve. Okay, so now what we're going to do is we're going to look at solving for that conservation of momentum. That means the momentum in the first object initially plus the momentum in the second object initially has to equal the momentum in the first object. Oops. The momentum in that first object finally plus the momentum in that second object finally. Now, what we need to consider about this question is, notice right here it says it sticks to a particle. So technically that means at the end, those two particles right, particle 1 and particle 2, they're going to be traveling together with some final velocity. What that means is, technically, are these two objects going to have a different final velocity? No. Really, VF1 and VF2 are going to be identical, right? If those two objects stick together, there's no possible way for them to be traveling at different velocities after that collision. Okay, so that means for this second part, we can almost consider that final velocity as just being the final velocity of both objects. There really is no VF1 or VF2. It is simply just V final. And you'll notice what that allows us to do is if both objects are traveling with the same final velocity, then you'll notice what that allows us to do is factor out that final velocity of that object. When I factor out final velocity, I really get m1 plus m2. Right? We're looking at solving for this final velocity. Right? So in order to do that, I'm going to divide out basically this combined mass of m1 plus m2. Right? And then I'm going to have to do the same thing to the other side of my equation. So really, I get that the final velocity of these objects is equal to that combined initial momentum divided by that total mass of your two objects combined. Okay, and again, this is where those directions that we've indicated at the beginning become very important, because if you don't indicate one of those velocities as negative, then you're going to end up with a greater initial momentum than we actually have, right? So your m1 is 4 kilograms, your vi1 is a positive 2 meters per second. We're adding that to our initial momentum of our second object, which is 6 kilograms times that negative 4 meters per second. And then that gets divided by our combined mass of 4 kilograms plus 6 kilograms. Okay. Which gives us 4 times 8 is a positive 8 kilogram times meters per second minus, right, we're going to get a negative here. So 6 times 4 gives me negative 24 kilograms times meters per second, all over that combined mass of 4 plus 6 is 10. So I end up with negative 16 kilograms times meters per second divided by our 10 kilograms. Right, your kilograms are going to cancel, leaving you in meters per second. And I get a negative 1.6 meters per second. Right, so you'll notice that your final velocity comes out with a direction. So these two objects, basically what it means is they're traveling towards each other, right? If VI1 has a positive initial velocity and VI2 is negative, it really means those two objects are traveling towards each other. And then, since that final velocity of the two objects is negative, it means that those two objects end up traveling in the direction that the second object was initially traveling. So our final velocity for those two objects is 1.6 meters per second, and we describe that as backwards. Okay, this conservation of momentum is really what's going to lead us into collisions in 5.3 and 5.4. Okay.